Okay, we're in section 2.7. We're going to change it up just a little bit, and we're going to talk about one of the applications of rates of change. Technically, there are still a few more derivative rules that we need to cover, but it's really something that can be done after this section, so we're going to come back to it. Okay, rates of change. Rates of change is a derivative. It's a slope. It's what a rate of change is. So we're going to use the derivative to calculate velocity and total distance traveled. Okay, so if we recall from previous sections, the derivative of f of x can be interpreted as the rate of change of y with respect to x. So in this section, we're going to look at one of the applications of that idea as it pertains to physics. So if s is f of t, and that's the position function, remember s for whatever reason is the position function, of a particle that's moving in a straight line. So this particle is literally like just moving in a straight line. Then the derivative, or delta s over delta t, it's not really the derivative, I'm sorry, that's the change of s over the change of t, that represents the average velocity. How does the position change over time? Okay, that's the average velocity over a time period. Whereas the instantaneous velocity is going to be defined as ds over dt. That's the derivative, so that is the instantaneous velocity. And that's the rate of change of displacement with respect to time. So with differentiation formulas learned previously, we're able to solve velocity problems now more easily, which is really nice. So basically, all that stuff is saying is, if you're given a position function, the derivative is the instantaneous velocity. Okay, you can do an average velocity by doing a change of position over a change of time, or an average velocity that way. But the instantaneous velocity is the derivative of position. So, that being said, again, this is not going to be a really long section. The position of a particle is given by the equation f of t equals t cubed minus 6t squared plus 9t, where t is measured in seconds and s is measured in meters. Find the velocity at time t. That's probably the easiest part of the whole thing. The velocity is the derivative of the position, which is going to be 3t squared minus 12t plus 9. And that's it. That's the velocity. Okay, and I'm pretty sure the next page is going to have us do a little bit more than that. So I'm going to try and remember that and copy that down on the next page. Velocity 3t squared minus 12t plus 9. Velocity is 3t squared minus 12t plus 9. Okay, so it says it wants us to find the velocity after 2 seconds. Well, that's pretty straightforward. We're going to plug in 2. Okay, let's see. If we plug in 2, doing a little mental math here, 2 squared is 4, times 3 is 12, minus 12 times 2 is 24. So 12 minus 24 is negative 12, plus 3, I mean, plus 9 is negative 3. So we're going to get negative 3 meters per second, because velocity has units, meters per second. Then it says, what is the velocity after 4 seconds? Well, that's just v of 4. A little bit more challenging here. Let's see if we can do this. 4 squared is 16, times 3 is 48. 4 times 12 is also 48. So 48 minus 48 is 0, plus 9 is 9. That actually wasn't that bad. 9 meters per second. Those weren't too terribly difficult. Part D says, when is the particle at rest? Well, at rest means it's not moving. If a particle is not moving, the velocity is 0. So we basically need to take our velocity function and set it equal to 0, because that's what we're trying to find. And the key here is that we're trying to find t. How do I know that? It says when. That's the question. So we're solving for t. That's the time. So we're going to take our velocity function, 3t squared minus 12t plus 9, and set it equal to 0 and solve. All right, so we're going to have to do a little bit of factoring here. It looks like I can factor a 3 out. That'll make it a little bit easier. T squared minus 4t plus 3 equals 0. This one actually looks like it's going to factor pretty nicely. It's going to be t, and then it's going to be minus 3 and minus 1. That should work out. So that means that t equals 3 or t equals 1 are the two t values that make this work. So our time, t equals 1 or 3 seconds when the velocity is 0 or the particle is at rest. Okay, and I'm going to tell you, at least from a perspective of AP, sometimes just writing this can actually give you points, as long as you understand that's what you're looking for when the velocity is 0, a particle is at rest. So that's important. All right, part E. When is the particle moving forward? That is, in the positive direction. Okay, we're actually going to do something that we haven't really done before. So we want to know when the particle is moving forward. That means that the velocity needs to be positive. So what we're going to do is we're going to create a number line for our velocity function. So we've got our velocity function. This is v of t. Okay, I know that the particle is at rest at times 1 and 3. The particle is not moving. In order for a particle to be moving in a positive direction, the velocity itself needs to be positive. In order for it to be moving in the negative direction, the velocity needs to be negative. We know that the velocity is not at rest anywhere else other than 1 and 3. We've already solved for that. So anywhere else, this thing has to be moving. And in order for it to change direction from positive to negative direction, it would have to stop somewhere. So the only places it could change direction is at time 1 and time 3. So what we're going to do is we're going to use a little bit of what's called sine analysis. We're just going to analyze the sine. I don't really care so much what the value is as much as I do what the sine of this thing is. So if I take some value left of positive 1, any value that I want to, the easiest thing to pick here is 0. If I were to plug 0 back into the velocity function, the 3 on the outside is 3 no matter what. If I plug 0 into t minus 3, it gives me a negative value. If I plug 0 into t minus 1, it also gives us a negative value. So I would get a positive from 3 times a negative times a negative. Two negatives multiplied together give you a positive, which means your velocity is positive anywhere left of time 1. If I were to plug something in between 1 and 3, like 2, into, again, my derivative, my velocity function, the 3 on the outside, that's kind of irrelevant. It's always going to be positive. But plug 2 into the first parentheses, you get 2 minus 3, that's a negative value. But then the second one, you get 2 minus 1, that's a positive value. So we get a negative times a positive, which means the velocity is negative, which means it is moving to the left. And then in the last one, anything greater than 3, plugging in like a 4 into both parentheses is going to end up giving you a positive value. So you get that the particle is moving to the right. Now we're going to assume, I don't know that it said so, we're going to assume that this thing started at time 0. It could technically have time in the past, but we're going to assume time 0 here for the starting point. So given the fact that at time 0, the particle must have already been in motion, it's got to be going to the right, because anything left of 1 there is a positive velocity, which means at time 0, this particle was moving to the right. So when is the particle moving to the right? From 0 all the way up until it gets to 1. Now I'm going to put a parentheses around the 1 because at 1, it's not moving right, it's not moving left, it's not doing either thing, it's stopped. So I'm not going to include the 1 as a positive direction. But then it starts to move again to the right after time 3. Again, at time 3, it's not moving, so I'll put a parentheses at 3, and then it's just going to keep on going to the right infinitely. So that's where the particle is moving in the positive direction. If it had asked us for when the particle is moving in the negative direction, it would have been from times 1 to 3, parentheses around both. It just didn't ask that. All right. Letter F. This is where we're going to have to kind of use our stretch the I don't want to say our imagination, but we're going to have to stretch things just a little bit because it wants us to draw a diagram to represent the motion of the particle. The problem is the particle is moving in a straight line. And the reason that that's an issue is because I can't really show very easily that this particle is going to bounce back and forth on the line without actually overlapping myself. You'll see what I mean. So we're going to say that down here this is 0. And we know that at time 0, so at t equals 0, the position of the particle is 0. How do I know that? Let's go back and look. I'm going to go all the way back. Well, I got to go even further. All the way back to the position function. The position function is given right here. And if I plug 0 in, I'm going to get out 0. So the position of the particle at time 0 is 0. Okay, that's why I know that. So the particle is going to start right here at position 0. Time 0, the position is 0. I got to find out when the particle stops and turns around. Well, we know it stops at time t equals 1. The question is, where is the particle? Once again, at time t equals 1, we have to go back to the original function. And I have to plug 1 in for t. That's going to give us 1 minus 6, which is minus 5, plus 9 is plus 4. So at time t equals 1, the position of the particle is at 4. So 1, 2, 3, 4. So at time t equals 1, the particle is here. T equals 1, s equals 4. So the particle has moved in this direction until we've gotten to here. Put little arrows on there just to indicate that was the motion direction, to the right. I know the particle moves back to the left at time from time t equals 1 to t equals 3. We found that in the previous part, in part E. Here's the part where we have to kind of stretch things a little bit. I can't make the particle go back straight to the left on my diagram because I've already got the arrows indicating it's going to the right. So while a particle is not technically jumping off of this number line, we're going to kind of curl it this way, even though it should really be on the line, but we just can't show that because it's not going to look right. So now we have to figure out where the particle is at time t equals 3. You got to go all the way back to the first equation, which I'm not going to do in this case. But if you plug in 3, you get out 0, ironically. So I know that the particle is going to be back here at 0. At time t equals 3, the position of the particle is 0. So it's going to go all the way this way until it hits 0. And then it's supposed to turn around and go back to the right based upon what we found. So I know it's going to keep going to the right, and it's going to keep on going to the right forever. It's going to go in that direction. Now, part G means, part G, we're actually going to have to figure something else out because it wants us to find the total distance traveled by the particle during the first 5 seconds. Well, we've kind of figured out some of that based upon the first 3 seconds, or at least we can figure that out from our diagram. If we want to figure out how far it's gone in the first 5 seconds, I have to know where it ends. I have to know where this thing stops at 5 seconds. So you got to go all the way back to the original problem and plug in 5 for t so we can figure out its position. And I've already done that. And the position of this thing is at 20, which is way out here somewhere. So when t equals 5, s equals 20. So it's going to be like way out here. I don't know exactly how far that's going to be, but it's way out there somewhere. So we're going to say that s of 5 is 20. Now that's not how far the particle has traveled, because we want to know the total distance this particle traveled in the first 5 seconds. Well, you can graphically look at this and say, well, it traveled 4 units to the right from 0, then it traveled 4 more units to the left, and then it's going to travel 20 units to the right. So it looks like it's actually traveled 28 total units. How do we actually represent that? Well, if you want to figure out the distance that something travels, you take its ending point and you subtract its starting point. So we want to figure out how far did this particle go on the time interval from 0 to 1. Why 0 to 1? Because that's the first time that it stops to turn around. Well, it went, let's see, where was this thing at time 1? At time 1, it was at 4. And at time 0, it was at 0. So 4 minus 0 equals 0. I'm sorry, equals 0 equals 4. Okay, then it turns around again at time 3. So from times 1 to 3, how far did the particle go? Well, at time 3, it was at 0, and at time 1, it was at 4. Well, the problem is here I'm going to get negative 4. But remember that if you're talking about the total distance this thing traveled, we don't really want to consider positive and negatives. We just want to have the positive distance that it traveled. So we actually take the absolute value of these values. So now it's the absolute value of 0 minus 4, which is 4. And then the last thing we need to do is we need to figure out the total distance that it traveled from 3 to 5 seconds, because it's heading to the right now forever. But we are only interested up until it gets to 5. So what was the position at 5 seconds? It was 20. What was the position at time 3? It was 0. So 20 minus 0 is 20. So it tells me, and again, you could have looked at your sketch to know this, it moved 4 units to the right, 4 units to the left, 20 more units to the right. So it moved a total of 28 units. And I don't remember if we had, yeah, I think we had meters in this case. So it'd be 28 meters. Okay, we're going to run through the next one much quicker. So again, find the velocity at time t. We're given another position function. So velocity is the derivative. So 3t squared minus 18t plus 15. Velocity at 3 seconds, plug in 3. And let's see, what's that going to be? It's going to be 927 minus 36 plus 15 is negative 12 meters per second, which just means at time 3 it's moving in the left direction or backwards. When is the particle at rest? That's when the velocity is 0. So we'll write that down just because you never know. So when the velocity is at 0, we're going to take 3t squared minus 18t plus 15, set it equal to 0. Factor out of 3. And then I'm pretty sure that this one also factors pretty easily. That should be t minus 5, t minus 1. So t is going to equal 5 or 1 seconds when the particle is at rest. That helps us because if we want to know when the particle is moving left or right, in this case, again, we're talking about a positive direction, we need to put the times where it's at rest on our number line, and then we need to check values around that. So again, I'm going to check 0 because that's to the left of 1. If I plug 0 back into my derivative, and the best place to do this is right in here because it's the most simplified form. If I plug 0 in there, I'm going to get a negative in the first parentheses and negative in the second parentheses. 2 negatives multiplied together give me a positive. It's moving right. In the second one, from 1 to 5, I'll plug in 2. I'm going to get a negative in the first parentheses, but a positive in the second parentheses, which is going to give me a negative. So it's moving left there. And then I'm going to plug in a 6 to the right of 5 there, and it's going to give me a positive times a positive. So again, the particle is moving to the right there. This is not always going to be the way it is. It just happens to work out this way in this case. So the particle is moving in the positive direction from 0 to 1, and then again from 5 off to infinity. That's where the particle is moving in the positive direction. Okay, let's go ahead and look at our diagram here. This one's going to be a little bit more challenging because I think that the values end up being pretty big here. So I'm going to kind of help out here and just know, because I already kind of know that I'm going to have to count by tens in order to make this work. 10, 20, 30, 40, 50, 60, 70, 80. That should be enough, I think. Whoops. Okay, so we're counting by 10. So the particle at time 0 is at 10. Okay, and again, I already know this stuff. That's why I'm telling you, but you would have to go back to the original. So at time t equals 0, the position of the particle is 10. It moves to the right until time t equals 1. The position of the particle there is at 17. Well, if that's 10, this would be 20. So 17 is about right there, I guess. So at time t equals 1, the position of the particle is 17. So it moves in that direction. All right. Must have done something good with sports there. Then it's going to go backwards until it hits time t equals 5. And I know that the position at time t equals 5 is negative 15. So that's actually, I probably should have gone even further back than I thought. That's going to be like right here. So at time t equals 5, the position is negative 15. Again, you have to go back to the original function, plug in time t equals 5, and that's what you get. So it's going to come back all the way to this, going that way. And then the particle is going to go off to infinity to the right forever. I think specifically, based upon what the next question asks, we need to find the time at, the position at time t equals 8. Plugging 8 in, not really something easy to do in your head, ends up giving you 66. So 10, 20, 30, 40, 50, 66 is going to be right about here. So time t equals 8. The position is 66. Execute order 66. All right. Find the total distance traveled now by the particle during the first 8 seconds. So again, you could do it by looking at your sketch and kind of counting the total distance, or the time from 0 to 1 is going to give us a distance of, let's see, at time 1 it was at 17, at time 0 it was at 10. Absolute value of 17 minus 10 is 7. Then it stops and turns around again at time 5. So at at time 5 it was negative 15 minus time 1, which was 17. So negative 15 minus 17 is negative 32, but the absolute value of that is positive 32. And then the last one's going to go from 5 to 8. The position of the particle at time 8 was 66, minus the position of the particle at time 5, which was negative 15. 66 minus negative 15 is positive 81. Absolute value of that is positive 81. So then we just add all the distances together, and we are going to get, what is that, 120 meters total distance traveled. All right, plenty enough for this one. Shouldn't be too hard of a section.